Welcome everyone. In this session, we are going to explore the concept of optimizing solutions. In the world of engineering and design, coming up with an idea is only the first step. The real work and the real magic happens when we take that initial idea and refine it. We aren't just looking for something that works, we are looking for the absolute best version of that solution. Over the next 15 minutes, we are going to look at how we move from basic evaluation to true optimization, using data, computer simulations, and systems thinking to solve complex problems. So let's start with a definition. What exactly is optimization? In casual conversation, we might say we are optimizing our schedule or our diet. But in engineering, it has a specific meaning. It is the process of moving beyond a solution that is merely good or adequate, and systematically working toward the best possible solution. It's not about guessing. It is about using data and models to improve a design systematically. We are looking for peak performance where all criteria are met and constraints are respected to the highest degree possible. This concept aligns directly with the science standard known as NGSS HS-ETS1-4. This standard focuses on using computer simulations to model the impact of proposed solutions. Why simulations? Because complex designs have many moving parts. This standard challenges us to analyze interactions within and between systems to optimize those complex designs. It asks us to look at the big picture, not just one component, but how all components interact with one another to create a final outcome. It is important to distinguish between two key steps in the design process: evaluation and optimization. Evaluation, often covered under HS-ETS1-4, is simply judging a solution's effectiveness. It asks, did this work? Yes or no? Optimization, which is our focus today, HS-ETS1-4, goes a step further. It involves taking that feedback and improving the design using data-driven insights. Evaluation is like a movie critic giving a review. Optimization is like the film editor cutting and refining the scenes to make the movie better before it's released. To perform this optimization efficiently, we rely on a specific tool: computer simulations. A simulation is essentially a digital model of a real-world system that runs using mathematical equations. Instead of building a physical object immediately, we build it in code. This allows us to predict behavior and outcomes before physical implementation ever happens. We can see how a bridge handles wind, or how a dam handles water flow, entirely within a virtual environment. Why do we rely so heavily on these simulations? There are two main drivers: speed and safety. First, speed. A simulation allows us to run thousands of tests in hours instead of years. Imagine trying to physically build 1,000 different prototype cars. It would take decades. Secondly, cost and safety. We can test catastrophic failures without risk or expensive prototypes. We can crash a virtual plane or flood a virtual city to see what happens, without hurting anyone or spending a penny on physical materials. The reason we need such powerful tools is that we are dealing with complex real-world problems. Simple problems have simple answers, but the problems we face today involve multiple interconnected systems without simple answers. You cannot just fix one thing without affecting another. A solution for one system can often create unforeseen ripple effects in another. We need to be able to see those ripples before they turn into waves that destroy our project. To understand these ripples, we must understand concept one. What is a system? A system is defined as a set of interacting parts forming a whole. Think of a car's engine. It's not just a block of metal. It's pistons, spark plugs, and fuel lines all working in unison. Other examples include traffic grids, river ecosystems, and electronic networks. In optimization, we can never look at just one part. We must look at how the whole machine functions together. Things get difficult when we look at the interactions between systems. Very few systems exist in a vacuum. For example, building a factory creates economic benefits. That is one system, but it also generates pollution. That pollution then interacts with a second system. It affects the river ecosystem. Furthermore, the trucks driving to the factory impact the city traffic grid. So one decision, build a factory, simultaneously impacts the economy, the environment, and the transportation network. This is exactly how simulations model interactions. A good computer model includes both interconnected systems simultaneously. It doesn't just calculate the factory's output. It calculates the pollution levels and the traffic density at the same time. This means that changing a variable in System 1 immediately predicts the impact on System 2. If we scale up the factory production in the software, we immediately see the fish population drop in the river model. This real-time feedback is vital. Let's ground this in a specific example. We are going to look at a case study, a new dam. Here is the scenario. A city has a problem. They need 500 megawatts MW of clean electricity, and they have a strict budget of under £1 billion. However, there is a major biological constraint. The project must not destroy the local salmon population in the river. This is a classic engineering conflict. Infrastructure needs versus environmental preservation. In this simulation, we are modeling two distinct systems. System 1 is the power grid. The variables here include water flow, the size of the turbines, and the total energy output. System 2 is the river ecosystem. The variables we are tracking here are water temperature, the speed of the flow, and the migration paths for the fish. Our goal is to find a setting where System 1 works without crashing System 2. We begin by running the simulation. Let's call this test number 1. We input the specifications for a massive 200-meter tall dam. The simulation crunches the numbers. The result? It produces 550 megawatts of power. This is great news for the city. The energy criterion is met. But then we look at the second system. The output shows the salmon population drops by 90%. This constraint is violated. It is an unacceptable solution. We solved the power problem, but created an environmental disaster. This brings us to the core of our lesson. This is optimization. We don't just accept the first result. We begin tweaking the model to find a better balance between all systems. We look at our variables. Can we lower the dam height? Can we add infrastructure to help the fish? We start testing variables like dam height and adding fish ladders for migration. We use the software to iterate, trying different combinations to see if we can get a better outcome. We move on to simulation, test number 2. We adjust the variables significantly to protect the environment. We lower the dam to 150 meters and install a fish ladder. The simulation runs again. The result? The salmon population drops by only 10%. This is a much better environmental outcome. However, look at the power generation. 480 megawatts power output. This is slightly low. We are under our 500 megawatts goal. We haven't quite solved the problem yet, but we are getting closer. Finally, we run simulation test number 3, looking for that sweet spot. We tweak the variables one more time. We set the dam to 160 meters, keep the fish ladder, and add a new operational rule, seasonal water releases. The result? We hit 510 megawatts of power, meaning our energy criterion is met. Simultaneously, the salmon population drops by only 5%. The constraint is met. By balancing the variables, we have found the optimized solution that satisfies both systems. Let's apply this logic to a different scenario. City traffic. This problem is equally complex, involving transportation, environmental quality, and economic systems. Every city wants to fix congestion. but they have competing goals. The goal here is to reduce commute times whilst improving air quality and keeping costs down. Often, doing one of these things makes the other worse, so optimization is key. We start by simulating traffic solutions separately. Solution A proposes building a massive highway. The model shows this results in 20% faster commutes, which is great, but it leads to 30% worse air quality. Solution B proposes a light rail system. The model shows this leads to 15% better air quality, but only makes commutes 10% faster. Neither solution perfectly hits the best possible outcome we are looking for. So we look at optimizing the traffic solution. We don't just choose A or B. We combine elements to find a new system configuration. We simulate a combined approach, building the light rail but pairing it with smart coordinated traffic signals for cars. The simulation shows that this optimized solution balances all three systems: speed, air, and cost, better than either solution could alone. We found a synergy that wasn't obvious until we modeled the interactions. To wrap up, let's look at the summary: why HS-ETS1-4 matters. We live in a complex world where systems are interconnected. We cannot rely on trial and error. Computer simulations let us test solutions safely, cheaply, and quickly. They give us the freedom to fail virtually so we can succeed in reality. Ultimately, optimization helps us find the best solution, balancing all system interactions. It ensures we don't just solve one problem while creating another. Thank you for listening.